What I want to talk about is something very specific and perhaps not very interesting, and something I think is very interesting, although not at all specific. So what I want to do is give you an extremely specific question about the unit disk with this metric I defined the other day, and will remind you of delta zero. But to put the question in context, I have to give you some background about reproducing kernel Hilbert spaces with complete Nevel-Pik kernels. And I want to give you a general context and general questions which motivate the very specific question. And then I will actually solve the very specific question. I will first develop some tools for working on it, and then I'll just go through an argument that's rather straightforward. And then I'll talk about how to move past the specific question, at least to something slightly more general. And then I will make some very unfocused general comments about the role of metrics such as the one we're talking about on reproducing kernel Hilbert spaces. So, I want to talk about the Dirichlet space. It's the space yesterday I called D0. It's the Hilbert space on the unit disk of holomorphic functions with that as its reproducing kernel. And you can also define it as the space of functions holomorphic on the disk for which integral f prime squared is finite. But I want to focus, I think, more now on the actual formula for the reproducing kernel, because that's what we use to define the metric. I also want to talk about the Drore-Arvidsson space. The Drore-Arvidsson space is a space of holomorphic functions in n dimensions. They are functions on the complex ball Bn contained in Cn. And again, I specified the space by defining by giving you the reproducing kernel. And it looks just like the Cauchy kernel, except that we're now in n dimensions. So this inner product Wz is now the dot product in n dimensions. And I want to allow n to be infinite, in which case Bn will be the unit ball in the little L2 space. So there's the formula for the inner product, and the comment that I'm allowing the infinite dimensional case. When n equals 1, this is not like the Cauchy kernel. It is the Cauchy kernel, and we get the classical Hardy space. However, when n is greater than 1, the space you get is not the Hardy space on the ball. The space is not defined by integrating mod f squared or mod f prime squared or anything like that. And the norm structure is a bit more mysterious, although you can give it explicitly as a Sobolev space or in terms of the moduli squared of the coefficients. And this Drore-Arvidsson space is going to play a big part in our story. And the reason is, here's a theorem. I will tell you in a moment where the theorem comes from, but for now it's just a theorem. It says there's a formula. The reproducing kernel for the Dirichlet space was given explicitly. It says there's a map phi of the unit disk into the ball, so that if I evaluate the kernel for the Dirichlet-Arvidsson space at the point phi of z, phi of w, I recapture the Dirichlet kernel on the disk. And the theorem says that for some n that is true, and the very specific question is, can I take n to be 1? And certainly in this formulation, the question seems arbitrary and without context. So what I want to do first is tell you a bit about the context. Now, whoops. So ignoring details, I want to tell you a bit about Hilbert spaces with complete Nevel-Pik kernels. There's a normalization in the theory that is best not focused on, And I will get rid of that normalization by supposing that the reproducing kernel for some space of holomorphic functions on the disk, the reproducing kernel for the origin is the function identically 1, in which case here's a statement that describes a Hilbert space with a complete Nevel-Pick kernel. It's a complete Nevel-Pick kernel if and only if 1 minus 1 over the kernel function, that's a function of 2 variables, is a positive kernel function of modulus less than 1. So positive kernel function means this function of 2 variables, x comma y. If I take a finite set of points and I look at b of xi comma xj, that should be a positive definite matrix for any set of n points. The examples, the easiest example is the Hardy space. 1 over 1 minus the kernel function is z bar w, and you just notice that it's a positive kernel function. A more sophisticated example are these generalized Dirichlet spaces that I discussed the other day. They have kernels 1 over 1 minus z bar w to the power alpha, and you undo the arithmetic to find out what b is, and you see that b is given by an expression involving a binomial to the power alpha, and you use the binomial theorem, and you write down the power series. You get a power series in z bar w with positive coefficients. So the fact that we have a positive kernel function follows immediately from the fact that we have a sum of monomials with positive coefficients, and we're inside the same world of things with complete Nevel-Pick kernels. Now, the Dirichlet space is of the same sort, but the argument is more delicate. Namely, again, you can write down explicitly what 1 minus 1 over k is, and again, you can compute the power series, but now it's a messy computation, and what you do instead is appeal to a statement about convexity of sequences of coefficients and the coefficients of reciprocals of analytic functions. And it's not a very long computation or a long analysis, and it all works out, but there's less intuition being carried along. And just to focus on the fact that there's something specific being assumed here, if you try and do the same thing for the Bergman space, where the kernel is 1 over 1 minus z bar w squared, you just compute b, and it's again a sum of 2 terms. Each is a constant times a monomial, but the coefficients are no longer positive. The coefficient of z bar w is negative, so that's not going to give you a positive kernel. The Bergman space is not in our class. Well, if I have a positive kernel, I can represent it. I have a positive kernel function on the space X. I can represent it by mapping X into a Hilbert space so that B of xy is the inner product of phi of x with phi of y. And when I unpack all that, it tells me that there's a structure theorem for such Hilbert spaces with reproducing kernels, namely the space H of functions on X has such a reproducing kernel if and only if there's some scalar function which we will remove with our normalization and assume to be 1, and there's a map from X into the ball so that the kernel for the space H, the reproducing kernel for the space H, is given by the reproducing kernel for the Dirichlet-Arvidsson space of dimension n, evaluated at phi of z and phi of w. Now, I said this is a structure theorem for a certain class of Hilbert spaces. That's completely unfair to the history of the subject and to the importance of that class of spaces, because what I've done is take this theorem and turned it into the definition. We've essentially defined the condition so that this theorem is true. Actually, complete Nevel-Pick kernel is defined by the validity of an abstract analog of the Nevel-Pick theorem about interpolating multipliers. And the theorem really is, if there's an abstract Nevel-Pick theorem for H, then H is of this form. But we can just take this as our definition and ignore all these questions about existence of multipliers. So the result I stated about the Dirichlet space, that result on the bottom, is just this abstract structure theorem applied to the Dirichlet space. The fact that the reproducing kernel for the Dirichlet space reproducing at the origin is identically 1 makes those betas disappear, and then we get what we had before. So the general question is, given a Hilbert space H to which this theory applies, what values of n can we take? And more generally, what kind of structural information can you get about this mapping that maps into the unit ball? How does that mapping relate to the properties of H as a Hilbert space? And one of the things I want to focus on is I raised these questions in the language of reproducing kernel Hilbert spaces and talked explicitly about the reproducing kernels. We can reformulate this without the reproducing kernels, because what we're doing when you unpackage the definitions is we're mapping x into the ball, and then we're looking at this space of functions that vanish on the image, that vanish on phi of x. That's going to be a closed subspace, or take its closure, and then look at the quotient of the big space by the space that vanishes on phi of x. That's some sort of space of functions on phi of x, although the norm is a little obscure. And isometrically, it's the orthogonal complement of the things that vanish on phi of x. So this function space on phi of x, namely v perp, is what we're getting as our representation for this abstract Hilbert space H. And that's what we're trying to understand. And what I want to say is that this construction interacts with these distance functions that I defined the other day. Recall the other day I said if I have a Hilbert space with a reproducing kernel, there is a naturally associated distance function. It's in fact the distance between x and y is the norm of the difference between the projections onto the associated reproducing kernels. And at this level of generality, you can already see some interaction between this distance construction and this fact about the Dirichlet-Arvidsson space. Namely, assuming for convenience that phi of x is a variety, it's the zero set of some multiplier, then we had this decomposition of, we get this decomposition of the Drury-Arvidsson space as J plus J perp. I'm sorry, this is the Dirichlet-Arvidsson space as J plus J perp. And it turns out, as we pass to J or pass to J perp, this distance function changes monotonically in ways that to me suggest facts about taking Hermitian vector bundles and splitting them into subbundles and the orthogonal complements of the subbundles and doing the bookkeeping about what happens to the curvature. But let me put all these general things aside. Let me make, though, the comment that I was talking about Hilbert spaces with complete Nevel-Linipic kernels. At this point, we can put that aside also. There's this general statement, you have a Hilbert space of functions on some x, and you have a Hilbert space, or you have a Hilbert space of functions on x tilde, and you map x into x tilde, and you construct things that vanish on the image of x, and then take the quotient of that in the big Hilbert space, and you get some space of functions on phi of x that are the orthogonal complement of things that vanish there. That construction is fairly natural. That construction shows up in other cases also having nothing to do with complete Nevel-Linipic kernels. The most well-known example of this construction is when I take the tensor product of H with itself, I can then embed, that's going to be a space of functions on x cross x. I can embed x in as the diagonal, and this is then the space described by Ehrenstein. The orthogonal complement of the things that vanish on the diagonal is the Hilbert space with the reproducing kernel whose square is the original reproducing kernel. That's just the comment that these constructions show up in other places. So there's this general question, given this kind of construction, what can you say about the relationship between the Hilbert spaces H and H tilde and the mapping properties of phi? And that's the general type of question we're talking about. Now, coming back to the specific question about the Dirichlet space, the specific question as formulated can be answered algebraically, because the hypothesis tells you that a certain thing is associated with this function b that's a positive definite kernel function. Such a function can be represented through a mapping into n-dimensional Hilbert space. That's an algebraic statement, and the rank of that kernel function is related to, or is defined to be, the dimension you can choose for that Hilbert space you're embedding in. And if b is given by a power series with non-negative coefficients, the rank is the number of non-negative coefficients, and in the case we were talking about, that number is infinite. So the only n you can choose is n has to be infinite. In other words, algebraically, you can see that the mapping where I said, is it possible to have the mapping with n equals 1? The answer is no. N has to be infinite. But what I want to do is find an argument for that that's more intrinsic to the Hilbert space theory, perhaps, and more robust to variations on the question. For example, where I could answer the question without having to find the explicit diagonalization of b, which is what I'm doing with the power series. So we're now going back to the original question. The theorem we started with was there's a mapping phi from the disk into some ball. The mapping is originally defined just as a set mapping with no assumption of smoothness. But as soon as you go back to the definitions of these distance functions delta, you see that the form of the mapping, the structure of the mapping, ensures that it's an isometric mapping from one space with the distance delta sub h1 to the other space with the distance delta sub h2. And that structural fact is enough to show that some maps can't happen. And that's what I want to talk about. How to use that structural information to show a certain map can't exist. So what I want to do is, suppose there is such a map, suppose the answer to the question, can n equals 1, is yes, and I'll start developing structural properties of the mapping in terms of these delta functions, and we'll get a contradiction. So what I want to do is understand the mappings geometrically, and the first thing I want to do is try and understand the metric associated with the Dirichlet space. The metric is just a distance function between 2 points, but it's most easily understood in terms of the infinitesimal Riemannian metric, which is given by some scalar multiple of the Laplacian of the kernel function on the diagonal times the arc length element. That computing the Laplacian is slightly awkward, but it's not hard to do the computation on the machine and see what the principal term is. And there's what the principal term is, this factor of log 1 minus mod z squared to the minus 1/2. As z tends to 1, this tends to log of 0, so the thing is blowing up. And that's, the denominator is the denominator that would be there if we did the computation for the Hardy space. That extra logarithmic factor is something new, and it's something that's giving you a fundamental difference from the Hardy space. So, we could also compute the Gaussian curvature. The Gaussian curvature is given in terms of lambda. It's essentially, whoops, I'm going the wrong way. Where'd lambda go? It's essentially Laplacian log lambda divided by lambda squared. So you compute and you compute, and you find out it's an awkward thing, but there's a principal term, which is scalar times log 1 minus mod z squared. So z is tending to 1 as you go toward the boundary. That's tending to negative infinity. So the Gaussian curvature of this is unbounded from below. And this is in contrast to those other function spaces we looked at where the Gaussian curvature was constant, except for the space with parameter alpha, it was the constant was 4 divided by alpha. And we're now looking at the limiting case, alpha tends to 0, And we're getting something where, first of all, the curvature is not constant, but more importantly for us, the curvature is unbounded below as we go to the boundary. And I cannot, but I would like to, understand the computation I'm about to do purely in terms of Gaussian curvature, but I don't know enough geometry. So what I want to do is look at circles centered at the origin. And I want to understand what their metric structure is in this geometry. So if I go out a distance from the origin, I go out to within 2 to the minus m of the boundary, then the distance in terms of delta d0 from the origin is approximately 1 minus 1 over m. This distance function is always between 0 and 1. It's tending to 1 as you tend out to the boundary, but it's tending to 1 at this rate that's rather different from what you've seen, that's different from what you would have seen if you were doing the pseudo-hyperbolic metric. And now I want to do a construction. I want to take that circle. This is the circle whose Euclidean radius is 1 minus 2 to the minus m, and I want to put 2 to the m equally spaced points on it. And I want to know how far they are apart, those equally spaced points, in this distance. And I'm not going to compute it exactly, I'm going to compute it approximately by saying the points are very close to each other in the Euclidean sense, so rather than use this metric, we can use the infinitesimal Riemannian metric as a good approximation, in which case the delta distance between the points is approximately lambda evaluated at that point times the Euclidean distance between them. And the Euclidean distance between them is on the order of 1 over 2 to the m. And that other expression I had is there was a 1 minus mod z squared on the bottom, which is 2 to the minus m. And then there was this negative 1/2 power of a logarithm on top. So I write all that down, I do the cancellation, I get 1 over root m. And now I know from the nature of the construction, oh, and next I want to assume the mapping phi takes 0 to 0. That is a convenience and I could work around it, but also the pseudo-hyperbolic metric is conformally invariant, and when you think about that a little bit, you see that that means that there would have been no loss in generality in taking phi of 0 equal to 0, which means this circle centered at the origin is not only going to have to go to a circle, because this map's isometric, but it's going to go to a circle centered at the origin. So what I have now is 2 copies of the disk, and I have one circle way out here, and I'm mapping it to one circle here, and the mapping is isometric, but it's isometric in metrics that aren't the standard ones, so I have to actually write down what's going on explicitly. I'm mapping 2 to the m points on that circle close to the boundary to 2 to the m points on the circle now with delta 0 radius, I'm sorry, delta 1 radius, is equal to 1 minus 1 over m. Well, delta 1 is the pseudo-hyperbolic metric, so the circle of that delta 1 radius, in fact, is the circle centered at the origin with that Euclidean radius. So it's that circle out there. And I'm putting 2 to the m points on there. I want to know how far apart they are in the delta 1 metric. And I go through the same type of computation as before. I have 2 to the m points. So the Euclidean distance between them is on the order of 1 over 2 to the m. And it says the pseudo-hyperbolic distance is on the order of m over 2 to the m. What is that? Oh, yes. That's the Euclidean distance. M over 2 to the m is the Euclidean distance between the points times the hyperbolic density out there, the pseudo-hyperbolic density. And you get m over 2 to the m. Well, so what have we done? We've mapped isometrically a set of points with spacing from each other 1 over square root of m to a second set of points with spacing m over 2 to the m. And we were free to take m large. The point of m large is basically that you can wash away all the details from the approximation statements, all the approximately and roughly statements get washed away by the fact that we were trying to map isometrically and we moved points with this very small distance from each other with this relatively large, distance from each other to points with that relatively small distance from each other. In other words, we're taking the points and we're moving them closer together. In other words, we can't have done this isometrically. And filling in the details, that says we couldn't have mapped the circle in the delta 0 metric to the circle in the delta 1 metric isometrically. Well, that's only the case n equals 1. But if you want to push further, you can see the same general pattern is going to work, except that you don't have such a clear geometry with circles. But if you just look not at the fact that the first circle is mapped to a circle, but that the first circle is mapped into the surface of a sphere of the appropriate radius, what you get is exactly the same kind of argument, but the number of points in the pseudo-hyperbolic sphere of the appropriate radius inside the n ball is not m over 2 to the m, but it's m to the a over 2 to the m, where a is some number that is the effective dimension in that Heisenberg type metric on the sphere inside the n ball. But again, as soon as you take m large, the fact that those two are comparable is no longer true and you get a contradiction. So that is the outline of a proof. And it's also the outline of a proof that m has to be infinite. And I said I wanted a proof that was a little bit more robust than just doing the algebra and finding that the diagonalization of the kernel of the B function required infinitely many coordinates. You can also push this forward and get, well, you get the same result for the D sub alpha spaces. More interestingly, you can get away from the Dirichlet spaces to some general spaces of Dirichlet type. Richter, Sundberg, Ellman, Shamorin have investigated spaces where here's the core of the norm for the Dirichlet space, the norm squared, with omega equals 1, but there are other choices for omega. For example, if omega is a positive harmonic function, that will give you another Hilbert space, different, but one which again has a complete Neville and a Pick kernel. So again, we're in the place where these questions make sense. And for appropriate weights. And again, you can ask the same question. And again, this proof can be modified to give you an answer, because all I really needed to know is, first of all, what the approximate distance is from the origin to a point out by the edge, and that distance is an explicit function of the norm of the reproducing kernel, and you can write down reasonably comfortably, reasonably sharp asymptotics for the norm of the reproducing kernel. And in fact, you didn't even need to know about this entire circle. All you were trying to do was show that you had a number of points out here, that you just take a subset of this, and the spacing of the points just on the subset, if you take points equally spaced and try and map into the ball, that's not going to work. So all you need is the same kind of geometric construction out here on some bit of arc, and that kind of construction is going to work on any piece of arc where omega is tame as you go to the boundary. In other words, omega is a positive harmonic function which need not be smooth up to the boundary, but as long as I have a segment of arc where it is smooth up to the boundary, I can, with a little bit of pain in finding the estimates, run the same kind of argument. Well, that argument was ad hoc, this taking a bunch of points in the circle and seeing what happens when you try and map them to the other circle. But the other underlying idea is geometric. I emphasized the fact that these things had negative curvature unbounded below. One of the geometric ways of understanding curvature, at least on these two-dimensional things, is that negative curvature says if you take a point and take a geodesic circle around that point, in the case of negative curvature, that geodesic circle is bigger than in the flat case. It's either bigger in the sense of area, or it's bigger in the sense of circumference, and the excess in both cases, when properly normalized, can be used to measure the curvature. And what we're getting here is that because the curvature is tending to minus infinity, informally at least, it means the circumference of the circle is going to be very long, much longer than it would be in the flat case, and in fact much longer than it is in the case of classical hyperbolic geometry. And the fact that you're trying to map this very long curve into the relatively shorter curve gives you an obstruction, because you're trying to do it isometrically. That kind of informal discussion about curvature I find very compelling, except that it doesn't really work so well for those intermediate Dirichlet spaces. And I think that's a reflection of the fact that my understanding of the geometry here is too superficial. In the last couple of minutes, I just wanted to make some remarks about some other metrics that show up when studying these things that are related. One metric I wanted to mention is the Gleason metric. The point I wanted to make now is the Gleason metric is defined on the spectrum of the multiplier algebra. But there's a natural inclusion of the disk or of the space X on which the Hilbert space is defined into the spectrum of the multiplier algebra. And on that set, you can define the Gleason metric just as the maximum pseudo-hyperbolic oscillation of a multiplier of norm at most 1. And it's a relatively elementary fact about Hilbert spaces with reproducing kernels that this has to be smaller than the metric delta. But in the case of Hilbert spaces with a complete Nevel-Linnapic property, well, first of all, why are these two statements equal? One is a statement about maximizing the modulus, given that you're 0 at a point. The other is a statement about maximizing the pseudo-hyperbolic metric. These two are equivalent because you can do compositions with linear fractional maps. If you're in the case where the norm of the multiplier is the suit norm, then composing with linear fractional maps isn't going to change the norm. Otherwise, you want to show that a multiplier of norm 1 composed with a linear fractional map gives you another multiplier of norm 1. That seems to be a version of von Neumann's inequality, which I mention only because it's not completely transparent that these two quantities are equal to each other. Anyhow, when you have a complete Nevel-Linnapic kernel, it's exactly the statement that these are also equal to that function delta. The complete Nevel-Linnapic kernel says that there is this upper bound for the oscillation of multipliers between 2 points, and in fact that upper bound can be attained. So this oscillation metric for the multipliers and this delta function are the same, which suggests that there's more to be said here about the relationship between delta in the structure. And this is just the statement that the Gleason metric has been studied extensively. I mentioned the other day that it's been studied extensively as part of studying the fine structure of H infinity. In the early days, after H infinity was a topic, when H infinity was a topic of great interest, there was a great deal of study of the spectra of other algebras of H infinity of other domains, again using the Gleason metric. But the Gleason metric is actually a more abstract concept. And it's some sort of generalized Harnack's inequality. And there are studies of the analogous generalized Harnack's metric where you put away the subject, the issue of Banach algebras, and you just take a vector space with certain additional structure, and you study metrics that you can build using Harnack's inequality and they, in certain special cases, reduce back to the Gleason metric. And I think my point here is there's a general functional analytic framework in which this type of metric shows up naturally. It also has a non-commutative analog for people who look at non-commutative function theory in the ball. And Popescu has been looking at this for some time, and he's got papers on what he calls the Harnack-Gleason metric on these non-commutative balls. The other comment I wanted to make, final comment, is there is ongoing work in studying several complex variables and studying the geometry of domains there's an ongoing program of using the intrinsically defined metrics on the domains to study the function theory and the operator theory and just the geometry of the domains themselves. The classic example is Poincaré's theorem that says that the two-ball and the bidisk are not biholomorphically equivalent. One way to show that is to compute what metrics, such as, for instance, the delta I described earlier, are in the two cases. Notice that certain metrics, such as those, would have to be biholomorphic invariants, and then notice that the structure of the metrics precludes there being a biholomorphism between the two. So there are these general studies of distance functions in several complex variables, and you'd like distance functions that behave monotone, that are monotonic under holomorphic mappings to the domains, and in particular interact very nicely with automorphism groups if there is a non-trivial automorphism group. And there are several fundamental domains that show up in the several complex variables world looking at these things. There's the Kara-Theodori metric, the Bergman metric, the Kobayashi distance. And I don't want to get involved in detailed descriptions of all of them, but I want to just indicate briefly how they are related to what we've been talking about. The Bergman space of a domain omega is an example of a reproducing kernel Hilbert space. It's not going to have this complete Nevelina-Pick property, but it is going to have the property that its multiplier algebra is H infinity. So the multiplier algebra is in this nice world of uniform algebras where there's a bit more theory. And the Bergman metric, in fact, is again going to be the infinitesimal version of this metric delta H. H is a Hilbert space with a reproducing kernel, delta H is defined, the infinitesimal version is Laplacian log of the kernel function on the diagonal, and that in fact is the definition of the infinitesimal version of the Bergman metric. So the thing we're talking about at one level is a generalization of the idea of the Bergman metric. The Kara-Theodori metric is another of these three metrics that show up commonly. The Kara-Theodori metric on omega turns out to be the Gleason metric, because the Kara-Theodori metric is defined as taking the supremum over bounded analytic functions, bounded holomorphic functions on omega. But we know that the bounded holomorphic functions on omega are the multipliers, so it's taking the supremum over multipliers. The Kara-Theodori metric is basically a question about mapping from omega into the disk and solving an extremal problem to get a distance. The other metric, and the one that is less clear in this context, is the Kobayashi metric. It goes in the other direction. The Kobayashi metric is the metric you get by solving an extremal problem asking about maps from the disk into omega. And it's in some sense the dual of the Kara-Theodori metric, and it's not so clear to me what the analog is of the Kobayashi metric in this context. So all I want to really suggest is there's some interesting relations between the operator theory and function theory of a reproducing kernel Hilbert space and these metric spaces, the underlying set X on which we've put this metric defined by the Hilbert space. And there's not much known how to pass information back and forth between the two categories. And it seems to me more specifically there's not much known about how one should understand the geometry on these metric spaces. There is a literature that I'm starting to try and learn about metric spaces and what curvature, how curvature could be defined on metric spaces if you don't have additional structures such as the Riemannian metric. So, thank you for your attention.